Hello everyone. Today we are going to study Unit 6, that is Demand Estimation and Forecasting, which is part of Block 2, Demand and Revenue Analysis. Objectives of this unit is that we should be able to identify a wide range of demand estimation and forecasting methods. And we should be able to apply these methods and to understand the meaning of the results. We should be able to understand the nature of a demand function, identify the strengths and weaknesses of the different methods, and understand that demand estimation and forecasting is about minimizing risk. What is the difference between demand estimation and demand forecasting? Estimation attempts to quantify the links between the level of demand and the variables which determine it. Forecasting, on the other hand, attempts to predict the overall level of future demand rather than looking at specific linkages. So estimation is actually the link. It tries to quantify the links between, say, X and Y, and forecasting is actually going to predict the overall value of future value of Y rather than looking at the linkages between X and Y. So in terms of forecasting the demand, or in terms of the managerial economics, we can say that we are interested here to predict the overall level of future demand rather than looking at the specific linkages. The set of techniques used may differ, although there will be some overlapping between the two. An estimation technique can be used to forecast demand, but a forecasting technique cannot be used to estimate demand. A manager who wishes to know how high demand is likely to be in 2 years' time might use a forecasting technique. A manager who wishes to know how the firm's pricing policy could be used to generate a given increase in demand would use an estimation technique. So for this reason, the firm needs to have information about likely future demand in order to pursue optimal pricing strategy. It can only charge a price that the market will bear if it is to sell the product. So basically what is happening is that suppose we are going for over optimistic estimates of demand, then that may lead to an excessively high price and the sales will be lost. And on the other hand, suppose we are going for over pessimistic estimates of demand, this may lead to a price which is set too low, resulting in lost profits. So the more accurate information the firm has, thus less likely it is to take a decision which will have a negative impact on its operations and profitability. The level of demand for a product will influence decisions taken by a firm regarding the non-price factors that form part of its overall competitive strategy. For example, let us take the case of the level of advertising carried by a firm. It will be determined by the perceived need to stimulate demand for the product. In other words, advertising will hopefully increase the demand for the product. However, advertising expenditure represents an additional cost. You all know that. That will be an additional cost to the firm. So unnecessary spending in this area needs to be avoided naturally. So if the firm's expectations about demand are too low, it may try to compensate by spending large sums on advertising. Money which in this example may be partly wasted. Alternatively, it may decide to redesign the product in response to this, thus incurring unnecessary additional costs in the form of research and development expenditure. Earlier, we studied price and cross elasticities, which can assist managers in pricing and income elasticity, can provide useful insights into how demand for a product will respond to different macroeconomic conditions. The assumption was that these elasticities were known, or that the data were already available to allow them to be easily computed. But usually this is not the case. For many business applications, The manager who desires information about elasticities must develop a data set and use statistical methods to estimate a demand equation from which the elasticities can then be calculated. This estimated equation is to be used to predict demand for the product based on assumptions about prices, income, and other factors. Now we are going to study in this particular unit estimating demand using regression analysis, evaluating the accuracy of the regression equation and regression statistics, the marketing approach to demand measurement, demand forecasting techniques, barometric forecasting, forecasting methods, regression models. Those which are written in red letters, I will go on study. I will discuss those things first. Then, if time permits, then I'll come back to barometric forecasting. And part of marketing approach also I'm going to tell you now because that involves forecasting. Other parts, if time permits, we'll go for that because this today's thing actually entirely quantitative part should be understood very clearly by all of you. Now estimating demand using regression analysis. Regression analysis we have already studied in block 1 unit 3. That is how to find out the how y can be regressed on x or x can be regressed on y. So they can also be used to estimate demand relationship. Example, consider a small restaurant chain specializing in Chinese dinners. The business has collected information on prices and the average number of meals served per day for a random sample of 8 restaurants in the chain. These data are shown in the following slide. I'm going to that. So regression analysis can be used here by to estimate A and B, that is A hat and B hat. We can use the regression analysis to estimate the coefficients of the demand function, that is quantity demanded is equal to A plus BP. Now, based on the estimated equation, we can also calculate the point price elasticity of demand at mean values of the variables. Now here, this is the table. We have it, this is in your book. So no need to discuss here this one. This is a table given for an example. Now here, now we can find out the values like Qi minus Q bar, Pi minus P bar, Pi minus P bar square, and Pi minus P bar into Qi minus Q bar from the given data. And below at the lowest row, find out the summation. These things are required for calculating the estimated value or regressed value. We need the extreme right column, the lowest, I mean, at the end of the column, we find that is the denominator value, sorry, the numerator value, and just next to that, you find that summation Pi minus P bar square, that is a numerator value. Now we can find the B hat and A hat respectively. So formula from block 1 unit 3, we had already studied. The left side yellow one is actually giving you B hat and A hat formula. And here we are estimating y on x, and right hand side is the derivation from the table. Qd is a function of price. So instead of y hat, we have to write Qd, and A hat, B hat, and for x we can write P. P is the independent variable, and Qd is the dependent variable. From the earlier slide, we find what are the values here. That is summation one is minus 1750, and the other one is 4000. And the Q bar, average Q is 100, and average price is 160. Average price is 160. Now from that, we can find out the equation, that is 170 minus 0.47, B hat is equal to minus 0.4375, A hat is equal to 170. So we can write down the regression equation, Qd is equal to 170 minus 0.4375 into P. And elasticity of demand is equal to dQ by dP by Q by P. Here we have taken the mean values or average values of Q and P. So that is giving you that is minus 0.7. So estimates the regression equation is estimated from the actual data given. Then from that we can find out the elasticity of demand. So now since the parameters A hat and B hat are estimated, the strength of the relationship between the dependent variable and the independent variable, in our example QD and P, can be measured in two ways. First is called coefficient of determination, which is denoted as R square, capital R square, to measure how well the overall equation explains changes in the dependent variable. Then there is another measure known as T statistic. T statistic is to test the strength of the relationship between an independent variable and the dependent variable. Now, testing the overall explanatory power, the square deviation of any yi, that from the mean y bar, mean that is y bar, is yi minus y bar whole square. That is known as the total variation in y. Total variation in y. Summation of all these square deviation, that is the variation in y for each value of y. Summation of all these square deviation for all values of dependent variable is taken as total variation. That is summation yi minus y bar whole square. Now, total variation can be split into two parts, or two components, can be separated into two components. One is explained variation and the other one is unexplained variation. So what is explained and what is unexplained? For each xi value, the predicted value of yi is yi hat, that we know. That can be computed by substituting xi in the estimated regression equation. Like here, qd is equal to a hat plus b hat p. Now p value is changing, then qd value, estimated value of qd is also going to change. So we can write down y1 hat is equal to a hat plus b hat x1, y2 hat is equal to a hat plus b hat x2, and yn hat is equal to a hat plus b hat xn, and so on. For every xi we can write that. Now the square difference between the predicted value yi hat or estimated value and the mean value y bar is defined as the explained variation. The word explained means that the deviation of y from its average value y bar is the result of changes in x. So the change in x, due to change in x, there is some change in y, that is the difference between y hat and y bar. So it is explained, it can be explained that y hat minus y bar change is possible because of changes in x. For example, the data on total output and cost used previously, earlier example, that price. One important reason the cost values are higher or lower than y is because output rates xi are higher or lower than the average output rate. Total explained variation is found by summing up all these squared variations. Now, unexplained variation is the difference between yi and yi hat. That is part of the deviation of yi from the average value y bar is explained by the independent variable xi. The remaining deviation unexplained value, the difference yi minus yes, that part is correct. That is part of the deviation of yi from the average value. A part of the deviation of average value y bar is explained by the independent variable. That part, if you forget, that is a repetition of that. Unexplained variation is the difference between yi and yi hat. The remaining deviation of yi minus yi hat is said to be unexplained. That means we don't know for what reasons there is a variation between the estimated value and the actual value. Summing these squares, we get unexplained variations. Now this is the diagram here. Suppose at OXI, AXI is the actual value, YI is the actual value. Now, estimated value at OXI is CXI, that is YI, Y hat. Sorry. Now, Y bar is equal to BXI, OY bar, that is Y bar is equal to BXI. Now, AB is the total variation, yi minus y bar. AC is the unexplained. We don't know why it is actually below the yi value. CB is the explained variable. Okay. Now the green one is actually hat minus y bar square, that is the total, variation, green wala. Then sorry, total explained variation yi hat uh, minus y bar. Some mistake I have done here while doing the graph. uh, No, it's correct. It's correct. Total variation is equal to yi minus yi hat. If the that is total variation. If the regression equation explains none of the variation in y, then r square will be 0. If the equation explains all the variation, then the coefficient of determination will be 1. Like in general, the higher the value of the r square, then the better the regression equation. The term fit or best fit, we know that is, best fit is often used to describe the explanatory power of the estimated equation. When r square is high, the estimated equation is said to fit the data very well. That means it's almost close to the data. A low r square would be indicative of a rather poor fit. That is not a good one. Now here, actually you don't have this xi part in the book. There is some printing mistake or it has been omitted wrongly. I don't know exactly. I have calculated this xi value from the given b hat and a hat value in the book, and that is the xi value is equal to, that is x is equal to output, y is cost, and y is equal to a plus bx. X value will be 0, 5, 8, 10, 15, 23, 25. Please read like that because it's not there in the book. Now we can calculate the regression equation, yi minus y bar, xi minus x bar. Then from the formula, we can find out, from this table, we can find out yi hat is equal to 87.08 plus 12.21 xi. There is another way of calculating the a hat, b hat, is that you can convert the equation y is equal to a plus bx into normal equation, taking the summation of the left hand side and right hand side. Summation yi is equal to na plus n stands for number of observations plus b summation xi. Then multiply y with x, then take the summation, that is summation xi yi is equal to a summation xi plus b summation xi square. Now these two normal equations, solve them just like your simultaneous equations, then also you will get the value of a and b directly instead of going for this formula. Suppose you cannot remember the formula, then you can go for this normal equation. This method also, it will give you the same result, a hat and b hat. It will be 87.08, that is a hat, and b hat will be 12.21. And from the table we have used the formula for b hat and a hat, and that also can be used and you will get the same answer. Now this one we are actually explaining total variation and explained variation and non-explained variations. Look at the figure here, yi minus y bar. Y bar is equal to 237.14. Yi minus y bar square. Then yi hat, that is the estimated value of yi, that is estimated value of yi when x is equal to 0. When x is equal to 0, actual value is 100. Here 100 actual value yi, and estimated value is actually estimated value is actually the third column. Second column is yi minus y bar. fourth column is the y hat, was 87.08. That is the estimated value. Actual value is 150. Estimated value is 148.13. Actual value is 160 value of y, and the estimated value is 184.76. It has come from from this equation 87.08 plus 12.21, and just put the value of x is equal to 0, x is equal to 5, x is equal to 8, and so on, and you will get yi hat value, and that I have done here. Now yi hat, then you take the formula. For the formula, you get unexplained variation and total variation, explained variation, etc. Now that can be used here. How high must the coefficient determination be in order that a regression equation can be said to fit well? There is no precise answer to this question. For some relationships, such as that between consumption and income over time, one might expect R square to be at least 0.95. In some other cases, such as estimating relationship between output and average cost for 50 different producers during one production period, an R square of 0.40 or 0.50 might be regarded as quite good. Based on the estimated regression equation, what we found earlier, that is yi hat is equal to 87.08 plus 12.21 xi. Now total explained variation divided by total variation, that is coming here. Total explained variation is actually that is 762.95.88, and the total variation is 79942.86, that is equal to 0.954. So that means the more than 95% of the variation in total cost can be explained by changes in output levels. Thus, the equation is a good fit, or the best fit you can say, because 95% of the variation can be explained due to variation in x. That is why it is one of the best fits. Now, evaluating the explanatory power of individual independent variables. Here we have to use the t-test. The t-test is used to determine whether there is a significant relationship between the dependent variable and each independent variable. This test requires that the standard deviation of the estimated regression coefficient should be computed. The relationship between a dependent variable and an independent variable is not fixed, because the estimate of B will vary for different data samples. From suppose 300, out of that you have taken a 50 sample, some another person has taken another 50 sample, then this will vary. So that for that reason, we have to 95%, we have to take the t-test. The standard error of B hat from one of these regression provides an estimate of the amount of variability in B. So the equation for this standard error is B hat stands for root over of the ratio. The numerator is summation yi minus y hat I square divided by n by 2, and denominator is summation xi minus x bar square, where n is the number of observations. For the production cost example in our earlier slide, n was equal to 7, and the standard error of B can be written, that is equal to, this is the formula is summation yi minus y hat square. This we can get it here, 3668.41 at right hand side. Then we can put it here, and this will come 1.19. And what about the second one? That is summation xi minus x bar square. That is here summation xi minus x bar square from the earlier table here. Summation xi minus x bar square 511.43. Look at this point. That is 511. It's not coming. I'm trying to use my pen drive. Sorry. Pen tab. Here. This is 511.43. Okay. Now let us go back to the formula. Yes, now it is becoming 1.19. So the least square estimates of B hat is said to be an estimate of the parameter B, that we know, but it is known that B hat is subject to error, and thus will differ from the true value of the parameter B. For parameter B, there can be n number of estimates depending on n number of samples. That is why B hat is called an estimate. Okay, because of the variability in V hat, it sometimes is useful to determine a range or interval for the estimate of the true parameter B. For that reason, we have to go for t-test. Using principles of statistics, a 95% confidence interval estimate for B is given by equation B plus Tn minus K minus 1 multiplied by S B hat. Now, Tn minus K minus 1 represents the value of a particular probability distribution known as student's T distribution. The subscript n minus K minus 1 refers to the number of degrees of freedom, where n is the number of observations or data points and K is the number of independent variables in the equation. In our example, n was equal to 7 and number of independent variable K was only X was the independent variable. So or only output was the independent variable, so K is equal to 1. So there are 5 degrees of freedom. Now we have to go to and search the T table, that is 95, n is equal to n minus K minus 1, that is equal to 5. So at 5 degree of freedom, 5, then we can find out the value. What is the value of that? Let us go to the T table. Here, T table, here you can go for, that is total for 95 degrees, 70, 95, yes, 95 is, and for 5, 2.571 here, that is 2.571. 2.571. So this value is the T value. Here, this side it is 5. This side you find, this side it is 5. Here 5. And this side it is 95 degree. 95 degree. 95 degrees coming here. 95 degrees of freedom. 2.5, 2.571. 95 degrees freedom. 95% confidence interval, sorry. There it is, 2.571. Okay. Now, so basically what is happening here is that estimated value of B plus minus, the repeated estimations of the output cost relationship, it is expected that about 95% of the time such that the true value of parameter B will lie in the interval defined by the estimated value of B plus or minus 2.571 times the standard error of B. So now 12.21 is the B value plus 2.571 into 1.19. 1.19, then that is equal to, or the value interval is 9.5 to 15.27. 9.5 to 15.27. Now this means that the probability that the true marginal relationship between cost and output within this range is 0.95. If there is no relationship between the dependent and an independent variable, the parameter B would be 0. A standard statistical test for the strength of the relationship between Y and X is to check whether the 95% confidence interval includes the value 0. If it does not, the relationship between X and Y are measured by B hat is said to be statistically significant. If that interval does include 0, then it is said to be non-significant, meaning that there does not appear to be a strong relationship between the two variables. The confidence interval for B hat, the output cost example, did not include 0, and thus it is said that B hat, an estimate of marginal cost, is statistically significant, or that there is a strong relationship between cost and rate of output. Another way to make the same test is to divide the estimated coefficient B hat by its standard error. The probability distribution of this ratio is the same as student's T distribution. Thus, this ratio is also called a T value. If the absolute value of this ratio is equal to or greater than the table value of T for n minus K minus 1 degrees of freedom, B hat is said to be statistically significant. Using the output cost data, the T value is computed to be B hat was equal to to 1, and SB hat is equal to, where is it? SB hat is equal to 1.19. Yes, here 1.19 below. Here, this is the result here. 1.19, and we can go for that is here mod value 12.21 by 1.19 is equal to 10.26. Because the ratio is greater than 2.571, the value of the t statistics, which 2.571 is the value of the t statistics, it is concluded that there is a statistically significant relationship between the cost and output. In general, if the absolute value of the ratio B hat by SB hat is greater than the value from the table for n minus k minus 1 degrees of freedom, the coefficient B hat is said to be statistically significant. So we studied t value, which should be statistically significant. In our example, here B hat is becoming statistically significant. Now the standard error of the equation is used to determine the likely accuracy with which we can predict the value of the dependent variable associated with particular values of the independent variable. As a general principle, the smaller the value of the standard error of the equation, the more accurate the equation is, and hence the more accurate any predictions can be made from it. It will be. To put this in another way, the standard error represents the standard deviation of the dependent variable about the regression line. The smaller the value, the better the fit of the equation to the data, and closer the estimate will be to the true regression line. Now, standard error of the coefficient works along the conversely, the larger the standard error, the bigger the deviation from the regression line, and the less confidence that can be put in any prediction arising from it. It gives an indication of the amount of confidence. I'm not going into this detail thing that is there in the book. You just read about it. Now I think you are clear about the regression, how to find out the estimate and how to find out the statistical significance of the estimate. There are a number of things to do. So it's 9.75, 95% interval. Yes, correct. Now, marketing approach. I'll discuss only the forecasting part so that we can discuss the other parts later on. This will be used for other sub divisions of your unit. So here, major thing is that vast majority of business decisions involve some degree of uncertainty or risk, and managers seldom know exactly what the outcomes of their choices will be, because we don't know what is there in the future. A firm or a businessman firm, he will just produce depending on his gut feeling, or maybe on the past data, what has happened, like that. He cannot predict the future. For that, actually, it needs a lot of it is actually involving a lot of uncertainty and risk. So one approach to reduce that uncertainty associated with decision making is to devote resources to forecasting. Forecasting involves predicting future economic conditions and assessing their effect on the operations of the firm. Future forecasting, actually, you don't have anything except the past information. You have to forecast or predict about the future on the basis of past information. That is the basic idea behind forecasting. You are taking a risk, but for that you are predicting something on the basis of what has happened in the past. So one should be very careful about forecasting also. There are different techniques for forecasting. We will go to that. The objective of forecasting is to predict demand. Sometimes managers are interested in the total demand for a product. For example, the decision by an office products firms to enter the home computer market may be determined by estimates of industry sales growth. He will depend on what has happened to the sales of the industry in that particular production field. In some other cases, the projection may focus on the firm's probable market share. That is also there. So the forecast suggests that sales growth by existing firms will make successful entry unlikely. The company may decide to look for other areas in which it will try to expand. So forecast can also provide information on the proper product mix. For example, for an automobile manufacturer such as Maruti Suzuki, managers must determine the number of Swift versus Alto to be produced other what produced to, so that they can be sold in the market. In the short run, this decision is largely constrained by the farm's existing production facilities for producing each kind of car. That is the short run situation. However, in the long run, managers can build or modify the production facilities. They have the choice, or they have the freedom, we can say. The long run is long enough so that they can take decisions. But such choices must be made long before the vehicles begin coming off the assembly line, or coming off to be sold in the market. So accurate forecast can reduce that uncertainty caused by the long. For example, if the price of petrol is expected to increase, then the relative demand for auto or compact cars or small cars is also likely to increase compared to Swift. So if there is a prediction that petrol price is going to increase, then the company may focus on producing compact cars like Alto, rather than on bigger cars like Swift. Okay, so forecasting is an important management activity. Major decisions in large businesses are almost always based on forecast of some type. In some cases, the forecast may be little more than an intuitive assessment of the future by those involved in the decision. In some other cases, the forecast may be required thousands of work hours and lakhs of rupees. Forecast may have been generated by the firm's own economists, provided by consultants specializing in forecasting, or be based on information provided by government agencies. You can also take data from government agencies for the forecasting of your production or market or whatever, depending on what you are going to do. Forecasting requires the development of a good set of data on which the analysis is to be used. So there are three important sources of data in forecasting. They are expert opinions, surveys, and market experiments. I will come back to it once I finish the regression part and forecasting techniques. That will be better, I think. Now, let us skip these things for the time being. Surveys, this thing, let us skip this for time, because come to demand forecasting techniques, because these are quantified information, and you have to use all these trends, seasonality, etc. So it is better if we discuss it first. So forecasting actually, here time series analysis is involved, because you are forecasting something over a time period. What is going to happen after 10 years, say, or after 5 years, like that. So regression analysis also can be used here, but here time is the independent factor. Instead of x and y, x is the independent factor, like output cost. Output was the independent factor, cost was the dependent factor. Now here time will be the independent factor. That is the idea behind time series analysis. Time is a variable here. So regression analysis can be used to quantify relationship between variables. However, data collection can be a problem if the regression model includes a large number of independent variables. When changes in a variable show discernible patterns over time, time series analysis is an alternative method for forecasting future values. The focus of time series analysis is to identify the components, or these components are actually known as they are disturbance components. You have to eliminate them one by one. Components of change in the data. Traditionally, are divided into four: trend, seasonality, cyclical patterns, and random fluctuations. So when you are calculating the trend, you are calculating the time, you are finding the time series analysis, you have to give importance to all these components. A trend is a long-term increase or decrease in the variable. The seasonal component represents changes that occur at regular intervals. Like in rainy season, there is a higher demand for chhatris. Or in summer, there is a higher demand for air conditioners, like that. So analysis of time series may suggest that there are cyclical patterns, business cycles defined as sustained periods of high values followed by low values. Business cycles fit this category. Finally, the remaining variation in a variable that does not follow any discernible pattern is due to random fluctuations. So trend, seasonality, then cyclical patterns, and random fluctuations. And various methods can be used to determine trends, seasonality, any cyclical patterns in time series data, and other random variables. However, by definition, changes in the variable due to random factors are not predictable. The larger the random component of a time series, the less accurate the forecast based on those data. Now, trend projection. This is very one of the most commonly used forecasting techniques. You may use it for your other papers also. This is actually a statistical method. So, time series data trend projection is one of these commonly used forecasting techniques. This approach is based on the assumption that there is an identifiable trend in a time series of data. Trend projection can also be used as the starting point for identifying seasonal and cyclical variations. Data in the next slide is a time series data we are going to see. Farms, suppose that is also from the book I have taken, farms quarterly sales over a 3-year time span. Here, data is used to illustrate graphical and statistical trend projection and also to describe a method for making seasonal adjustment to forecast. Now, statistical curve fitting. This involves using the ordinary least squares concept developed earlier to estimate the parameters of the equation. Suppose that an analyst determines that a forecast will be made assuming that there will be a constant rate of change in sales from one period to the next period. The farm sales will change by the same amount between the two periods. The time series data are to be used to estimate that rate of change. Statistically, this involves estimating the parameters of the equation. St is equal to S0 plus Bt. Look at the equation, it is equivalent to Yi is equal to A plus Bxi. But here, time t is the independent variable, where S denotes sales and t indicates the time period. The two parameters to be estimated are the value of S0, which is equivalent to A in our earlier example, and B is the your coefficient, or you can say S0 hat and B hat, that way. The value of S0 corresponds the vertical intercept, just like your A of the intercept the line, and the parameter B is the constant rate of change and corresponds to the slope. Now here, this is the data. Now 4 quarters, 2019, there are 4 quarters, 2020, there are 4 quarters. This is a hypothetical time series sales data. The actual sales were actually 300, 305, 315, 340, and so on till 445. Now let us now give numbers to the periods 1, 2, 3, 4, 5, 6, 7, like that. Let us give numbers, then that becomes our T. Now here, T, then you can go through the same method, T minus T bar, ST minus ST bar, T minus T bar square, T minus T bar into ST minus ST bar. Then below, at the end of the table, look at the figure. I have calculated it, and it has come to 1832. Then T minus T bar square. Then you can do this 1832 divided by 1143. That will give you the value of B, that is 12.811. And S0 is equal to the earlier formula you can use. That is 281.390. So this can be found out. In the book, there is not there period for period 1 to 12 numbering is not there in the table, but it is written there. For your convenience, for our convenience, actually, I have done this, and you can go through this table. And here, this is the way we are using the same regression analysis, but estimating the value, but time period. You have, instead of X, you are taking a time period, and year wise, suppose quarter 1 is 1, quarter 2 will be 2, quarter 3 will be 4, and then 2019 quarter 1 will be 4, will be 5, 2019 quarter 2 will be 6, and so on. So you are going to get 12 time periods. These are actually T. Now from that you can calculate this. So based on the data from the table, the equation is estimated as 281.394 plus 12.811 T. The interpretation of the equation is that the estimated constant rate of increase in sales per quarter is 12.811. Why per quarter? Because we have taken 1 quarter as equal to 1. Just 2 quarters is equal to 1 plus 1 is equal to 2. So the constant rate of increase in sale will be, for every quarter, there will be an addition of 12.811 lakhs of sales. That is the idea. That is the forecast. Forecast or estimated value. A forecast of sales for any future quarter. Now let us say, suppose this is the example here. Here the figure is only up to 2020 quarter 4. The figure is only up to 2020 quarter 4. But suppose we want to estimate or we want to forecast the third quarter of 21. Third quarter of 2021. Then what will happen? 2020 is the 12th last. 2021 first quarter is 13, 2021 second quarter is 14, 2021 third quarter is 15. So our t value will be 15. Now we substitute that in place of t, we can write 281.394 plus 12.811 into 15 or 4 rupees 473.56 lakhs. So if at the end of third quarter of 2021, the forecasted value or expected sales will be 473.56 lakhs. This was not there in the table. In the table, data is only up to 2020. On the basis of that, there is a forecasting taking the time period, and we can say that the sales in at the end of quarter 3 of 2021, the sale is likely to be rupees 473.56 lakhs. Suppose that an individual responsible for the forecast wants to estimate a percentage rate equation anymore. So the parameters of this equation cannot be estimated using OLS because it is not linear. OLS is possible only when there is a linear relationship between x and y. So because the problem is that the equation is not linear, we cannot solve this problem here. However, we can convert it to say we can convert it to a logarithmic function. There is a simple transformation of the equation that allows it to be estimated using ordinary least squares. We have to take the help of logarithm. Now let us take the natural log of both the sides of the equation st is equal to s0 into 1 plus g to the power t. You know what is natural log? Natural log st will be equal to log s0 plus natural log 1 plus g to the power t. That will be again converted into log st in the natural log st is equal to natural log s0 plus t into natural log 1 plus g. Now you all know logarithm, and from logarithm this formula can be calculated. Look at this equation. Here it is linear in the form of y is equal to a plus bx. Natural log st is equal to y and natural log s0 is equal to a, and natural log 1 plus g is equal to your b, and x is equal to t, or independent variable is equal to t. So the key is to recognize that the sales data have been translated into logarithms. Here, if you're taking the logarithm, you can find out the value that is G. So instead of ST, it is log ST. So now here for the first quarter of 2018, the data to be entered are in natural log 300 is equal to 5.704 and 1, period is 1 and T is equal to 1. For the second quarter, natural log 305 is equal to 5.720 and period is 2, T is equal to 2 and so forth. The transform data are shown can be, so YT, this is the transform data. Okay, this is the natural logarithm of the sales, that is of each quarter. This value we already know the value of this. You are taking the natural logarithm of the sales, then you are going to get this one. Okay, now this is the natural log or in ST, and here that is ln ST. Okay, now these parameters are generated from logarithms of the data. 1 minute. Second quarter. Okay, now putting the natural log from values, you can find out the table and you can find out the estimated value YT is equal to 5.6623 plus 0.03531T. This is in terms of natural log. Okay, now this is the formula, this is the table, and for interpretation in terms of the original data, they must be converted back based on the relationship natural log S0 is equal to Y0 and B is equal to your natural log 1 plus G is equal to 0.0353. Now taking the anti-log yields, S0 is equal to 287.810 and 1 plus G is equal to 1.0359. Substituting these values for S0 and 1 plus G is equal to 1.0359 back to the original equation. Back to the original equation means this equation here. This equation here. This equation. That is ST second one. ST is equal to S0. ST is equal to S0 and where is it? The second one here. This is the equation. So putting that value, we are getting 287 is the sales in lakhs of rupees and in period 0, that is the first quarter, and the estimated growth rate is 3.59%. To forecast sales in a future quarter, the appropriate value of T is substituted into the equation. For example, predicted sales in the third quarter will be, that is 15th, third quarter means of 2021, and the T is equal to 15, then that will be equal to 28.7.810 into 1.0359 to the power 15 or 488.5 lakhs. So that will be the value or predicted sales with a growth rate of 3.59%. Now, seasonal variation in time series data. Seasonal fluctuations in time series data are not uncommon. In particular, a large increase in sales for the fourth quarter is a characteristic of certain industries. Like indeed, some retailing firms make large amounts of their total sales during Diwali period. Electric companies serving hot, humid areas have distinct peak sales periods during the summer months because of the extensive use of air conditioning and so on. A close examination of the data in our example, slide number 42. Look at the slide number 42 here. Look at this close examination. Here there is a big fluctuation. Like quarter 4 is very high, 340, 390, and there is 445. But other periods it is very low. It is not, it's low compared to the fourth quarter. Let us come back to our figure, our discussion here. Okay, so a close examination of the data in our example indicates that the quarterly sales increases are not uniformly distributed over the year. The increases from the first quarter to second and from the fourth quarter to first tend to be small, while the fourth quarter increase is consistently larger than that of other quarters. That is, the data exhibits seasonal fluctuations. Pronounced seasonal variations can cause serious errors in forecasts based on time series data. For example, the slide number 42, suppose let us say slide number 42. here. Now here, what is happening? Look at the figure, what is happening? The 300, 305, 315, 340, and let us come back to this figure. Remember that figure, or you just use your book, and we find that the increases from first quarter to second, and from the second quarter to fourth quarter is actually tend to be small. Now the figure, look at the figure there. It indicates actual sales for the fourth quarter 2020 were 445 lakhs. But if the estimated equation is used, slide number 43, to predict sales or estimated value for that period, using the constant rate of change models, the predicted total is actually coming to 435.13 lakhs. Look at the estimated value 435.13 lakhs and look at the actual sales 440,445 lakhs. This gap between actual and predicted sales occurs because the equation does not take into account the fourth quarter sales jump. There is a jump in the fourth quarter sale. The equation doesn't take into account of that, or doesn't take that into account. Rather, the predicted value from the equation represents an averaging of individual quarters. So the sales will be underestimated for the strong fourth quarter. Conversely, the predicting equation may overestimate sales for other quarters also. So the accuracy of the forecast can be improved by seasonally adjusting the data. Probably the most common method of adjusting is the ratio to trend approach. Its use can be illustrated using the data from our example based on the predicting equation, actual and calculated fourth quarter sales as shown in the next slide. Seasonal adjustment can improve forecast based on trend projection. However, trend projection still has some shortcomings. One is that it is primarily limited to short-term predictions. Now here, this is the figure for 2008, for 2018. We have taken the forecasted fourth quarter sales. We have taken only the fourth quarter sales. Let us go back to slide number 42. I have given the orange color or yellow color, that is for 340, 390 and 445. 340, 390 and 445 here. So 2018 fourth quarter, 2019 fourth quarter and 2020 fourth quarter. Look at the figure. Forecasted actual figures are 340, 390, 445. Average is 391.67. But the forecasting, depending on the estimated value, we got the value that is we discussed earlier. ST is equal to 281.394 plus 12.811T, and estimated values are 332.64, 383.88, 335.13. Average is 383.88. Actual divided by predicted fourth quarter sale is 1.022, 1.016, and so on. So here the final column of the table is the ratio of the predicted sales for the actual to predicted sales for the fourth quarter. This ratio is a measure of the seasonal error in the forecast. Here, the 3-year period, we see that average actual sales for the fourth quarter were 102% of the average forecasted sales for that quarter. The factor 1.02 can be used to adjust future fourth quarter sales estimates. For example, if the objective is to predict sales for the fourth quarter of 2020, what will happen? The predicting equation generates an estimate of 435.13 lakh. But let us multiply this with 1.020. That is the average ratio, actual divided by predicted. And multiply that, you are getting rupees 443.8 lakhs, which is actually closer to the actual sales. Because it was seasonally, that time there was a jump. Because of that, our estimation underestimated that 435.13. But if you are removing the seasonal fluctuations, then it is jumping to 443.8 lakhs, which is almost nearer to 445. So this is a similar technique could be used to make a downward adjustment for predicted sales in other quarters. Now, exponential smoothing. This is known as exponential smoothing. The trend projection is actually just regression analysis. I don't know whether time will permit me analysis where the only independent variable is time. One characteristics of this method is that each observation has the same weight. Now here we have to give different weights. Like in some cases, more recent observations will contain more accurate information about the future. Now, exponential smoothing is a technique of time series forecasting that gives greater weight to more recent observations. That is the idea, and this is the formula. First step is to choose a smoothing constant. The constant must be alpha, which must be less than 1 and must be greater than 0. And if there are n number of observations in time series, the forecast for the next period, that is n plus 1, is calculated as a weighted average of the observed value of the series at period n and the forecasted value for that same period. Fn plus 1 is equal to alpha xn plus 1 minus alpha fn. Fn plus 1 stands for the forecast value for the next period, and you know all these you can read from the book. So the forecasted value for Fn and all the earlier periods are calculated in the same manner. We can calculate this. Now note that equation cannot be used to forecast F1 because there is no X0 or F0. This problem is usually solved by assuming that the forecast for the first period is equal to the observed value for that period. That is, F1 is equal to X1. Using the equation, it can be seen that this applies that the second period forecast is just the observed value for the first period. The exponential smoothing constant chosen determines the weight that is given to different observations in the time series. As alpha approaches 1, more recent observations are given greater weight, and so on. You can go for this way. This is the table here. This method is referred to why this method is referred to as smoothing technique. Consider now at point alpha is equal to 0.20, at alpha is equal to 0.40, at alpha is equal to 0.60. There are different estimates. You find that much less fluctuation. Note that the smooth data show much less fluctuation than the original sales data. Note also that as alpha increases, the fluctuations in the FT increase. Now here choosing the constant, which one will be chosen? Here you have to use this formula, that is summation xt minus ft whole square, and for that you can choose. And here this table clearly tells us that 0.60 provides the best forecast using the data. Now evaluation of exponential smoothing, that you can read because it is given in the book clearly. Barometric forecasting also, it is manageable, you can understand this, no problem. Now forecasting method, here we have to use regression models, and this is the from the book. I have taken the sky, that is sky output, sky foods, big sky foods, and this from the Excel you can find out the regression data, and you can, this is here Q is a function of P, that is price, own price, then income, then price of other commodities. Now here, assuming that BSF plans to price at 5.85 next quarter, and then that is the regression data, Q is equal to 15.939 minus 9.057. You can find it out. Now the suppose left hand side shows that 5.85 is required. Then you just put the value 5.85 and 4800 income forecast, you can put that, and PC 4.99, you can put that, and that will become 31.565. So with an economic forecast provides a projection for income and an exponential smoothing model that provides a projected value for the competitor's price. Now here we can say that we can go back to the survey. I don't think there is much time for me as already. Okay, now you can go through the survey part, and that part you can read, no problem. That is usually statistics. I concentrated on the regression and forecasting part because these are very important. So we have looked at a range of demand estimation and forecasting techniques which can be used by the farm either singly or in combination in order to predict the level of demand for their products. The choice of technique will depend upon the resources at the farm's disposal, the cost to the farm, and of the insufficient knowledge of the market in which it operates, and the ease with which information can be obtained. Each of the methods considered here has its own advantages and disadvantages in its use, and there is no right or wrong approach. So as a general principle, you can say The more accurate information the farm has, the better able it will be to take the best decisions possible for the farm's efficient operations. Sales forecast can be developed using qualitative methods such as expert opinion, the Delphi method, or market surveys. Those you can discuss under the forecast and survey, etc. Those are there, and or by using quantitative models such as exponential smoothing, time series decomposition, or multiple regression analysis. I emphasized on a quantitative side, and also I discussed about the forecast and the expert opinion and survey. The market survey can be studied by you on your own. It is not that difficult, and the major part, I mean the quantitative part, I discussed because it will be helpful for all of you. Thank you.